see if I can find my pointer thingy. So remember when we talked about those weather balloons that carry the gizmos up in aloft to see what the temperature is, they see what the pressure is if you're going vertically. The weather balloons get larger. And so actually we talked about this the other day. We talked about the different ways of expressing humidity because, you know, notice that the mixing ratio is the same. Let's see, mixing ratio stays constant, okay? The absolute humidity changes because the volume changes, but the mixing ratio stays constant. Remember what the mixing ratio is a ratio of water vapor to 1 kilogram of dry air. But my point here is expanding, okay? So when we talk about clouds, we need to talk about reaching 100% relative humidity. And I'll remind you that we said, and I was going to pull up a slide, but if you want to reach 100% RH, your options are to cool it down or add water vapor. Those are your two options. This option is going to cool it down. So we're going to talk about how you make clouds by cooling down a cloud by making a chunk of air rise. I'm going to try to convince you of this. So this kind of talks about how that works. Why, when a chunk of air rises, why does it cool down? Well, it expands, okay, and kind of the reason it expands is the air gets thinner, and so basically up there there's fewer particles to kind of keep the parcel tidy. There's less pressure, so it expands into that less pressure. You're like, well, how does that help? Okay. Well, I have it on the next slide how to kind of talk you through that. But if you can get it, and we'll talk about lifting mechanisms, I think in part 5, in chapter 5, unit 2, or still unit 2. But if you can get a chunk of air to rise, it will expand and it will cool. And if it can cool to the basically dew point temperature. And the dew point temperature is 100% relative humidity, so it's cool. It reaches a certain temperature as it cools for condensation to begin. This video, I think, emphasized that most of the clouds actually have flat bottoms because it's that sweet elevation that basically that chunk of air has risen and expanded to cool down to reach 100% relative humidity. It's right at that point, right at that elevation. We call that the lifting condensation level. Okay. Okay. So diabatic versus adiabatic. I've been teaching this class for maybe 13 years or so, and I really kind of struggled with these two terms, but they're really not that complicated. Diabatic transfer of heat is basically what you do when you go to a stove and you want to heat a pan of water. That's diabatic. Basically, your pan of water is your system, and you're taking heat from your oven and you're putting it into your system. Okay, basically you're infusing it from the outside. Adiabatic, an adiabatic temperature change is one in which the system basically is kind of changing its temperature in and of itself. There's nothing to cross the boundaries. That's an adiabatic process or an adiabatic temperature change. So honestly, as we talk about, and I kind of have this little chunk of air in my hands, okay, and as it goes up, it expands, there's like an invisible boundary, and there's no heat coming in or there's heat going out, but the thing's cooling down, okay? And so we call this adiabatic cooling. Okay, so as my hands go up, they get further apart, it gets bigger. This is adiabatic cooling. And I'm going to tell you, actually, here in a few slides, that if you can get a chunk of air to go down, it's going to contract, and it's going to be adiabatic warming. Okay. So what's driving this cooling? If you can get a chunk of air rising, it expands. Well, the thing about expansion is that expansion actually is work. So basically, you have this chunk of air with an invisible boundary. Okay, expansion is work, and according to the laws of this universe, according to thermodynamics, that work needs to be funded by something. You can't just do work and have no energy to do the work. So basically, that work is funded by the kinetic energy or the temperature of the gas particles or the water particles. So as it expands work, it's actually doing work within its chunk of air, and that's actually work is funded by, like I said, the kinetic energy of the parcel of air. Okay, so As it goes up, it expands, it cools down. Pretty good. And since it's all kind of within that chunk, there is no, it's like a magician, there's nothing that crosses the boundary, basically. That's why we call it adiabatic cooling. Okay. So, do you guys, to kind of link it into something we talked about before, do you remember when we talked about the environmental lapse rate? I'll go ahead and put this on the board. This is unit 1. We said that if you send up a balloon, a weather balloon, we said kind of the usual ELR, that's environmental lapse rate. Usually. Now, actually, I think I told you in Unit 1, I'm going to have to come back and fix that. I didn't entirely lie to you, but I did a little bit. The usual ELR, the cooling, when you go up in the troposphere, is 5 degrees Celsius for every 1 kilometer you go up, usually. Okay. Now, we've got another lapse rate here. Instead of the environmental lapse rate, it's the dry adiabatic rate, okay, but it's another rate. Dry adiabatic rate, we abbreviate it DAR, stands for dry adiabatic rate. And this is exactly what we've been talking about. If you can get a chunk of air to rise, it will expand and cool 10 degrees Celsius for every 1 kilometer it rises. So this is going to kind of talk you through what that looks like. Okay, we have high pressure, air is thick, down low, air is thin, up high, and actually that's what's driving our expansion. So here we have the dry adiabatic rate in action. At the ground level, it's 32. You get it to rise 1,000 meters, the same thing as 1 kilometer. It goes from 32 to 22. We get it to go up another kilometer. Now it cools another 10 to 12 degrees Celsius. Another kilometer, it cools to 2 degrees Celsius. So that is the dry adiabatic rate in action right there. Okay. So as it rises, it will expand and cool. And like I said, if you can get that same chunk of air, sometimes there are definitely mechanisms to do this. If you can get that chunk of air to fall, it's going to actually squeeze together and it's going to warm. Okay. So one of the things on the slide, if you want to, which I wish I had, I would put DAR, dry adiabatic rate. Now, the environmental lapse rate, the ELR, will change. This thing changes. And I'm going to say this thing right here is constant. Okay. All right. Very good. Okay. So now we're going to switch it up a little bit. That last example, we took that chunk of air. I like what your author does. I like what meteorologists do, kind of take a little chunk of air and kind of showing it, kind of a little invisible boundary there. But now we're going to take a chunk of air and we're going to actually let condensation begin. Okay? Now, the thing about condensation, do you remember when I put solid, liquid, gas? And basically, if something goes from a liquid to a gas, you have to add energy. And if something goes from a gas to a liquid, energy is released. We call this latent heat. Both of these are latent heat. But the thing about when condensation happens within a cloud, this goes on, energy is released, and basically that warms your cloud. It warms your cloud. So the thing can go ahead and rise, but you kind of have, and expand, but you have a new rate because you kind of have energy released. And so it doesn't cool at 10, actually it cools at about 5. Okay? But if this is, you're going to see here in a minute some diagrams where basically you start it with a parcel of air, it gets bigger, okay? At some point, and it cools down, at some point it's going to go ahead and your cloud is going to begin to form. And this happens because basically it has cooled to less than the DPT, dew point temperature. So this elevation is what we call the lifting condensation level. That's the elevation you need, that's the flat bottom of your cloud. All right. So back to, we can do this whole lifting condensation level. At this point, basically, what happens is you have heat being released, so it can go ahead and climb, but if you have condensation going on, which you will, then it's going to expand, but it's not going to cool as much, okay? So that rate in general is what we call the wet adiabatic rate, or the WAR. So right here, I'm going to put WAR, wet adiabatic rate. That happens when condensation is occurring, and that is, you can go ahead and it will cool, but it will not cool at 10 degrees Celsius per kilometer. It will cool at 5 degrees Celsius per every 1 kilometer it rises. Okay. Again, I said the DAR is constant, the dry adiabatic rate is constant, the WAR is constant, sort of. Here in a minute, or in this part, I'm going to convince you that your author changes from a wet adiabatic rate of 5 to a wet adiabatic rate of 6 here in a little bit. I tracked it down once upon a time, and there is that wiggle room out there. But it is a constant. If you have condensation going on, and if you have lifting going on, then it's going to cool at this rate. All right, so let's see what that looks like. Again, I like the little hash marks, or every 1,000 meters or 1 kilometer. So we start with a chunk of air, 32, and only when you see cloud does it cool at the wet adiabatic rate. Here it's the dry adiabatic rate. Okay, so here about 3 kilometers, you see the little base of a cloud. So now it's not going to cool to negative 8. It's actually only going to cool to what, -3. Okay, because we have condensation going on there. Still condensation from 4 kilometers to 5 kilometers. So now it's going to still cool at this rate, this wet adiabatic rate. So it's not going to go -3 to -8. Okay, so that's kind of how that whole thing works. So, yeah. And clearly marked on here is the lifting condensation level. So you would say that's what, 3 kilometers or 3,000 meters is the elevation, the level, the elevation that condensation began, the LCL. Okay, so I guess it's in this part that we talk about how do you get a chunk of air to rise. Okay, well, we're going to talk about each one of these, I think, but you can force it against a mountain. We have here in the United States, we are under the influence of a prevailing westerly, mid-latitude westerly. So, of course, we have a mountain range over here. This is great for orographic lifting. The next one, and we'll talk more about weather fronts in here, but cold air, I'm going to tell you, you probably figure cold air is more dense than warm air. So actually that's a way to kind of get air to rise. Convergence is basically where you have air kind of meeting all up at one point and lifting where it meets. And then we've talked a little bit already about this idea of you can have, and you're going to see the same figures, I think, freshly plowed field, nice and dark, versus something else that has a different texture that's lighter around it. The sun beats down on the dark region, you can actually get some sort of chunk of air rising because it's hotter because of the albedo Okay, it just sucks up more energy, and it heats the air. That air becomes warmer, and it rises. So starting with orographic lifting, orographic uplift, this always reminds me of the like the vacuum cleaner. I know, probably. But this kind of makes sense. Basically, if you slam air against a mountain, it can't go through the mountain, so it goes up. And as it goes up, it's going to expand, and as it expands, it's going to cool. And if there's some moisture there, it can go ahead and cool to the point where condensation can 100% relative humidity. So the thing is, though, and you're going to see it on this picture right here, downwind on the other side, like if this is the Pacific Ocean, this is the Sierra Nevada range here, the Rockies, and then what happens is it dumps its precipitation over here, okay? It rises, expands, forms cloud, drops its precipitation, and then over here, it doesn't have any, it's dry when it goes on the other side of the mountains. So this is kind of a compare and contrast sort of thing. This is on the windward, this is on the leeward side. They're both pretty. Okay, so that's one way to get a chunk of air lifting, so there's 4. The second one is frontal lifting. Now, we'll talk more about weather fronts. We already have a little bit. Weather fronts, I remember the red one with triangles, I think you told me was the cold front. The blue one, the red one with semicircles is the cold, warm front. The blue one with triangles is the cold front. Yeah. So the thing about fronts is, and I don't think I'm going to show both fronts here on the next slide, but with your cold front, cold air is being aggressive. With your warm front, warm air is being aggressive. But with either front, you can get this sort of lifting mechanism. If you kind of think of it with the cold air being more dense, hugging the ground, and the warm air going up and over one way or the other. So it looks like this. This could actually go either way. It could either be a warm front or a cold front, depending upon which is being more aggressive. Usually, and I see kind of this looks like some thunderstorms here. And a lot of times thunderstorms, I think, are most likely associated with a cold air mass being aggressive, so it would be a cold front. But you see the cold air hugging the ground and the warm air kind of being pushed up or going up and over. And so it's that kind of lifting of the warm, potentially moist air. And so as it lifts, it expands, and as it expands, it cools, and it can go ahead and cool to reach 100% relative humidity. Then you can get condensation, and we're going to talk more about going from condensation within a cloud to going to precipitation. We're going to talk about that. But you can possibly get some precipitation. The third one is convergence, and this is where sometimes, and we'll talk more about convergence later. It's a player, but I kind of think if you put, you know, with little kids you could put candy, but with like adults, I guess you'd have to put money. If there was like a bunch of money right there, everybody would, like, maybe depending upon how desperate we were for the money, but everybody would go for it. Okay, so that's convergence. As everybody goes for it, it kind of builds up with people, and I guess that's where the analogy kind of ends. But it's the convergence actually that starts the moving upward in the middle. So there's different ways to get convergence, not just with money and with candy. But this is actually convergence of a wind going from the water, which is smooth, to the land, which is rough. And it's kind of like if you were to, let's see, I don't know what a good example. Well, if you were to go from ice, if you were skating, you were going to go from ice to the land, okay, the edge of the ice or whatever, which was rock or sand or something, grass. You'd go, whoo, and then you'd hit the grass and go, okay? You might go a little bit, but you'd be like stalled out a little bit. You kind of build up. That's the convergence. That's how that's working. So we kind of have that sort of thing going on in Florida, kind of on an ongoing basis. And the fourth way to get a chunk of air to go up is, again, what we talked about before. Basically, they call it localized convection because there's kind of some region that is warmer than than its surroundings. And a good way to me that you can get it warmer is you can actually have some sort of texture difference or color difference that basically, kind of from left to right, you see over here, it's like, you know, sucking up the solar energy. So this is a hot spot, okay? And since it's hot, it basically makes the air around it hot. And air that is warmer, and we're going to be talking more about this, air that is warmer than its surroundings, okay, make this blue, it's colder, is actually going to rise, and that's what you see it here, going up. Okay? And as it rises, it expands. As it expands, it cools. And so notice that what your author's done here is to go ahead and make a nice flat bottom on that cloud, okay? Because that is the elevation, that's the altitude that you needed to rise it to and expand and cool to reach the dew point temperature. So kind of what we've been talking about is this would cool at 10 degrees Celsius per kilometer, the dry adiabatic rate, and then up above here, it's going to cool at the wet adiabatic rate of 5 degrees Celsius per kilometer. All right. So I think the video we watched kind of mentioned these thermals. Okay, so that last one, the localized convective lifting mechanism. A few things is it can be good if you're trying to kind of clear the air, okay, to try to kind of get rid of your pollutants. Okay, it definitely, thermals create what we call an upward gradient. Basically, you have air relocating upward. And what do we call air relocating? Wind. So you kind of have kind of a gentle wind going up. It's actually called a kind of an updraft. And raptors, birds of prey, will try to kind of find these thermals. Skydivers, no, the hand glider people try to find these thermals and use them to their benefit. Okay. So I think that's a good place to take a break, and we will come back because this is a good pausing place.